Yeah. Oh, were we saying yeah. This, if all goes as planned, should not take very long at all. So this is something that I would have taught you back in Algebra 1, just for the record. So it is, I'm not trying to say that, that not to be rude by making you do work from the past, but I think that we really will struggle with a lot of what we do if we don't bring these topics back up to the surface. So today we're going to talk about vertical line test. Really, we haven't really talked about it yet, but we need to get right to the heart of what does it mean to really be a function. It's one of those things, again, that we talked about in Algebra 1. And I think that the brain, as it gets more developed, is more willing to receive an actual understanding of what a function is. So in ninth grade, we learned it as just the vertical line test. And maybe now we can think of it on a little bit more of a grander scale as to what it really means. So we're going to talk about the vertical line test, like is something a function or not a function. And then, of course, we're going to just quick talk about the domain and the range. And everything that we talk about today is in graphical form. So I'm just going to sketch some graphs. These will be a little bit hard. I'll try to be sympathetic to the fact that you're not using graph paper. So these are notes that get difficult to take because I have an advantage where I can just go like this and poof, I have graph paper. And that's going to be a little bit of a harder ask for you guys. So you might have to like label some points as we go. But I think once it comes back to you and you remember what we're actually doing here, then you might find the notes to even not be all that important. So here's a little x-axis and a y-axis. And there's, again, just three kind of main topics for the day. And if any luck, this takes 10 minutes and you're good. And then I can just shut up and let you work. So topic number 1 is when I make a graph like this, is it a function? So we use the word a lot, like we always function, graph the function, graph the function. But I mean, at the end of the day, that word carries some weight, some significance. What does it mean to be a function, or is this a function? So it's been a while, huh? So hopefully this will come flooding back to you. A function, and you don't have to write this down. A function is a relation in which each input has only one output. In other words, what that means is that for every x value on the graph, there's only one y value. The way we assess that is back in the day, hopefully, hope you remember this at least vaguely. We scan it with what's called the vertical line test. And the reason the vertical line test is significant is because you notice as I move this vertical line across the red graph, does my vertical line ever hit the red graph more than once at a time? Then this is a function. So to be a function means that you can't have any y values that are above and below each other. Because if you did, like for example, I mean, this is random, but if I just threw some rando point like right here, boop, and I said, hey, that purple point is now a part of the graph. It's no longer considered to be a function because if I went to this place right here and I asked you, so let's say that this is a function. I'll just name it f of x. In the past, before that purple point was there, if I had said to you, find the value of f of -2, that would have meant something. You could go to -2 on the x-axis and you could have found me the height of the red line. You could have gone to -2, which I'll point to it for you. It's right there. And before I put this crazy purple point up here, you could have said, oh, the function has a value that I can see right there. And I would have guessed that f of -2 was like, I don't know, maybe we'll just estimate like -0.5. But what problem happens when I add the purple point? If I say to you, what's f of -2 now, what's the issue that arises? There's two y values to choose from, and no longer is something considered a function when you have output options. You should always be able to look at a graph and find one output value for any input value. If there's ever a decision to be made, it's not a function. And that's kind of, I don't think that's that hard to understand. And so if I made another graph, so anyways, the red one was a function until I messed it up with the purple dot, right? But as it was when I graphed it like that, it's a function. Um, let's do another one, just a sketch. X-axis, Y-axis, and a pretty common, bless you, is something like this. Is that a function?
No.
Clearly not, right? And if you understand that whole thing about the vertical line test, then you understand how laughably much this is not a function. For God's sake, not many things can fail the vertical line test, quite frankly, worse than this one does. At any point, this is the only point right here where I'm wiggling this line around. This is the only point on this graph that passes the vertical line test. The vertex of that sideways, that inverted parabola. That's the inverse of y equals x, or y equals x squared. And so that right there passes the vertical line test. But as soon as I start to slide the line over, you see it is constantly failing miserably. So what we come to remember about function versus not a function is that if there's any part of the graph that exists above or below itself, then it's not a function. Does that so far make sense? If I wanted this not to be, if I wanted this to be a function, and this is sort of a hint of things to come, but if I said to you, come up here with a magic eraser and make this a function, then what you could do is you could actually erase this part of the graph. And now is that a function? It is. So what we're going to start doing eventually here in a couple of days is we're going to start taking a function, something that is a function, and we're going to restrict its domain. That'll make more sense in 5 minutes, so that when we invert the function, the thing that we turn it into is also a function. The goal will become, can I take something that is a function and make it so that when it effectively falls on its side, it is still a function? So that might be a lot for your brain to take in, but so you're going to see all sorts of graphs on the worksheet, and I'll just sketch a couple of them up here real quick. But the first question that is going to keep getting asked is it or is it not a function? And that is just a quick yes or a no. You don't have to write like a complete sentence, just yeah, it's a function, no, not a function. So the next topic up is domain and range. So does anyone have any vague recollection of what a domain is? Say that again. Mm, no. So the domain of a function is the set of all of the x values that it essentially is defined over, that it occupies. It's a very simple concept, really, once you're ready for it to be simple. And you went through the same thing with me 3 years ago when we talked about this in the Algebra 1 class, that at first when I tried to explain domain, it sounds really, really weird. But what domain really boils down to at the end of the day is think of it like you got a vertical line here and you got a vertical line here, and all you're simply going to ask yourself is, where could I place those vertical lines that would trap the whole graph? Think of it like a vice grip. And so as I'm coming in from this side, you would agree that the graph begins its existence at that line and that it ends its existence at that line. Like no one could possibly say that's not true. So that those two green lines represent what we call the domain. The domain, we could say, is anything in between the two green lines. If you have a piece of function, a piece of graph that has a defined value for an x coordinate, then that x coordinate is in what we call the domain. Now, if we were talking in casual English, which we can get away with sometimes, but in math, sometimes we have to say things fancier. The domain, I would look at this very casually, and I would, in plain English, say to you this: the domain goes from -5 to 4. And if you don't know what I mean by that, just take a look. I mean, this line is positioned 5 units to the left, and this blocker line is positioned 4 units to the right. So in casual English, I could say, yeah, the domain just goes from -5 to 4. I don't really want to move on, though, until you understand that. That's the furthest left and the furthest right that the graph goes, -5 to +4, right? So what we're going to do is we're going to express our domains in terms of what we call intervals. And so in math, you might recall, I think we did some of this in algebra 2. Don't know if it was algebra 1 or algebra 2, but at some point we learned how to do intervals. And the way I would write the interval from -5 to 4 is like this. I would say first off, capital D for domain. And now I'm going to make an interval, and it's going to look like this. Square bracket, -5, comma, 4, round bracket. So let's talk about that notation that we just used. Anyone want to take a stab, a guess as to why? Now, I'll accentuate something that will hopefully give you a pretty good hint here, but anyone know why it's a square bracket on the left side? Nope.
The circle's filled in.
Because the circle's filled in. And we ask ourselves the question, like we know this from like the olden days, that if a graph has a number that's like on it, if the graph makes it there, then we think of that as like, oh, it could equal that as well. That colored in circle says that that curvy zigzag graph, it gets to -5. So that's why in math, and if you guys are taking this class, there's a pretty good chance, so maybe a few of you are taking it because your mom said you had to, but there's a pretty good chance that if you take a class like this, that you're inclined to take more classes like this as they get harder and harder. And everyone's going to expect that you know interval notation. So moving forward, understand this. The square bracket implies the graph made it there. There is a defined value at that X value. And of course, now the cat's out of the bag. What does the round bracket imply?
The graph.
It didn't make it, did it? And we've seen this before with inequality things, that when we want a graph to get right up next to something but not quite get there, we put an open circle there to show that it didn't quite make it. So the rounded bracket is an implication that the graph starts there but not technically there, like infinitely close to it but not on it. So from this point on, that's going to be notation that you're going to use is the square bracket, round bracket notation. That's called interval notation. There's other ways to do it using inequalities, but we won't talk about that today. We'll just kind of cross one bridge. So that's the domain. It's a very simple concept. How far left, how far right. Now, if we switch to a different concept called range, for range, we have to change our perspective. If domain is X values side to side, what do you think range is? Y values. And so my two blocker lines, those two lines that I drew, those green guys, they're now purple and they're horizontal. And I want them to be horizontal because now they're going to vice grip down on the graph from above and below. And so if I grab this top line and I vice grip it down, I stop right there because that is the highest the graph ever goes. And then I grab this other line and I vice grip it onto that because that's the lowest that the graph ever goes. We're not going to sit around and draw lines. I mean, these are just for illustrative purposes. But the idea behind domain and range is I'm just asking myself, over what intervals does the graph exist? So with domain, we study the graph horizontally. With range, we study the graph vertically. So for the range, I ask you this, simple English. What's the lowest Y value that the graph ever obtains? Good. Does it make it? Yes, there is nothing in the graph to tell us that it doesn't. Like just because there's not a big colored in circle, we can see that the graph gets down to -1. And it happens right where that purple arrow is pointing. So the range bottoms out at -1. And because it makes it, what kind of boundary am I going to use? Square. So I want a square bracket at -1, comma, and how high does the graph go?
5.
To 5. Does it make it? Then it's also squared off. So there's your reintroduction to domains and ranges. And now what I'm going to throw at you is just some different sorts of sketches. And then I've got a whole practice packet full of them. You'll be really good at this by the time you're done. You'll be really good at it probably by the time you're halfway done, quite frankly. So yes, it's a function. Domain is this, range is this. That's just kind of be the theme for the day. Is it a function?
Yeah.
Yeah. Now let's talk domain and range. So this time, if I tried to employ this idea of my vertical lines, I used green last time, so I'll use green again. If I try to trap this graph, I can trap it here. What issue do I run into on the other side? It's going to go forever. There is no trap. So this line on the right-hand side it doesn't make sense. It doesn't have a purpose here. So this is an unbounded domain. This is not a domain that goes from point A to point B. This is a domain that goes from point A to something called infinity. And so if I wanted to write the domain on this one, where would be my first number? -1, 2, 3, 4, 5, 6. And I know it's hard again for you to do this on your own paper, but that right there is -6. And so the domain begins its existence at -6. And if I get my blocker line out of the way, you can probably see better. Does it get there? Not in this case, it doesn't. And so I'm going to say a round bracket. It looks like a parenthesis, right? In interval notation, it's just a round bracket, -6. And how far to the right does it go? As far as time will allow, which is called infinity. And so if you're a little rusty on your infinity signs, don't worry, you're going to get really good at drawing them again. So remember, it's just a little sideways figure 8. Okay, let's talk range on this function. And it's just simple questions. We're not building bridges here, engineering rocket fuel, like we're just asking ourselves left to right, low to high. What's the lowest y value this graph ever obtains? -4. And it does get there, so I'm going to go ahead and square bracket that one off. I can see that there's no one gave me an indication of it not reaching the bottom. So it does make it as low as -4. And again, if you're at all confused, that's this point down here is obviously the lowest, and it's at a y value of -1, -2, -3, -4. Hence that. And how high does this guy go? Infinity. And infinities always have round brackets. Why do you suppose that is? Because you can't reach it, right? You cannot get there. And so that's the definition of the round, is our way of saying you didn't make it, and you cannot make it to infinity. It's impossible. So let's do one more example. Maybe a couple. I'm sorry. I think I just thought of 2 things that I need to say. So sorry. Function? No. Okay, we get that out of the way quick. It's not a function. Let's talk domain and let's talk range. Remember, domain, if you just keep it simple, don't overanalyze everything. Domain is left to right. So when I start my domain and I write it down, D equals or D colon, whatever, what's the furthest left this graph ever goes? Correct. And the reason I wanted to do this example with you is because I find myself often where people put infinity, it needs to be -infinity. Remember that we have to differentiate between going forever to the left and forever to the right. -infinity has to be denoted as such. How far to the right does this graph go? To 0. Very good. Does it make it? Yeah, we'll just assume that it does. So we're going to square bracket that one off. Okay, let's talk range. How low does it go? -5, does it get there? It does. And this time me went out of their way to make sure you saw that it does get there. So generally with endpoints like that, we like to put dots there. If it's just a part of the curve itself, then we just make assumptions. So this does get down as low as -5. So I'm going to square bracket down at -5. And then how high does it go? Yeah, regular positive infinity this time. The last one I want to show you is it's either going to be a circle or what we call an ellipse. I mean, ellipse is just what we lazily called sometimes ovals. They look like ovals. So, last one, and then I'll just get out of your way here. And prepare yourself. You're about to see some really bad artwork. And I apologize in advance. It wouldn't be the first time that I've tried to draw something and it hasn't looked particularly well. So apologies in advance. In fact, I should elongate this more. Get it a little bit way up here. So what is that? Oh yeah, I just made my life a lot harder by trying to draw this. Let's see. Oh, whoop, sorry. Ooh, come on, little buddy. Ooh. It's not terrible. I don't know what happened over here. It's like I just was quickly abducted by aliens or something. So you'll see some graphs like this. First off, is it a function? Oh, no, not even close, right? This terrible failure. So when we talk about domain and range, remember we're just simple words, left, right, low, high. So for the domain, how far left does this graph go? To -1, right? And does it make it? It sure does. How far right does it go?
5.
5. Good. And it does make it again, despite my artistic shortcomings. And then the range is just low to high. I just wanted to put one of these because I give this assignment out sometimes and people think like, oh God, it looks like a lemon now. What do I do? It's like, listen, the question doesn't change. Left to right, low to high. Keep it simple, right? What's the range? How low does it go? -1, 2, 3, 4, 5, 6, 7. Good job. You knew and I didn't even know. I drew the red lemon thing. How high does it go?
5.
I believe you're correct. And that's that. So that's not going to cover one more. I'm sorry, one more. Oh, I don't lie to you on purpose, for the record. I don't do that, but sometimes I just forget stuff and then I go, oh, snapdragons. The last thing I want to say is this. What do you do if you see a graph like this? And by if, I mean when. The red graph, is it a function?
No.
Right. This is the literal definition of something that you could not be more non-function than a vertical line, for God's sake. Nothing can fail a vertical line test worse than a vertical line. So no, this is not a function. What is the domain? Yeah.
3.
Yes, 2, I think is what you meant to say. And listen, here's the deal. Would you agree that this entire graph exists at an x coordinate of 2? Then we don't call this an interval. I knew what you meant, but we don't call this an interval from point A to point B. We use a curly bracket and we make a set and we say the domain consists of one number and his name is 2. Curly brackets are the notation that we use when we're about to write someone a list of things. And if something only has one, it doesn't make sense to say, I mean, someone would accuse you of heavy drug use if you said, oh, it's the interval from 2 to 2. You know what I mean? People give you weird looks when you say stuff like that. So instead of thinking of it as an interval, we just call it a number 2. That could be confusing. I hope it's not. Fire away.
For the range, would it just be a set of infinite?
Yes, this range would be a set from -infinity, not a set, but excuse me, an interval from -infinity to +infinity. Because height-wise, it goes forever down, forever up. But width-wise, it exists in one pocketed place at the number 2. So you guys got it? That took way longer than, but that's all that you've been hanging around with me for a while. If I say 10 minutes, I mean like 24. So I'll give you your assignment and then you can work the rest of the hour on either this one or the Delta Math one. I don't care. Either way.